Hi, welcome back for part two of Common Sense Knowledge and Reasoning class at the ALPS Winter School. So, in the previous segment, we discussed how we can do common sense reasoning as a generation and discussed the three flavors of unsupervised inference time algorithms spanning across neural search to classical discrete search and things in between, and how that can draw best lemonades out of off-the-shelf neural language models. But none of these will be enough because lemonades are lemonades and has a lot to do with the limitation has a lot to do with the current paradigm of deep learning, where we tend to achieve human level or even superhuman level performances on leaderboards by combining these two: supervision on a lot of exam problems and self-supervised learning a lot of raw text. However, this recipe fails, as we saw last time, on generative evaluation such as abductive reasoning, counterfactual story revision, and various constrained text generation tasks, which require logical constraints. And very briefly, last time we also discussed how humans cannot learn in this mode of supervision on a lot of exam problems or self-supervision on a lot of deep learning code. Because as a human, if we really want to learn uh, hard concept like deep learning, we do need to class. We want to take we want to see lectures, we want to read the tutorials and textbook. So humans really learn efficiently because of our access to declarative knowledge, not just lots of raw data or lots of exam problems. And so the question is, how do we do that for deep learning neural language models as well in particular? So part two is going to be about how we might do declarative knowledge, how we might teach neural models with declarative knowledge for the purpose of knowledge modeling beyond just language modeling. And so starting with Comet Atomic 2020 to appear at AAAI this year, well, let me give you some brief discussion on the precursor work, which are Atomic and Comet. So starting with Atomic, which is an atlas of machine common sense for if-then reasoning. Let me first define common sense, which has been implicit or somewhat explicit in the previous segment, but that's basically the basic level of practical knowledge and reasoning concerning everyday situations and events that are commonly shared among most people, implying that we are not limiting ourselves to knowledge that every single person in the universe agrees with. And for example, it's okay to keep the closet door open, but it's not okay to keep the fridge door open because the food inside might go bad. But as discussed in part one, all of this can be defeasible with additional context. So, for example, if the fridge is empty and not even plugged to the wall, then who cares if you keep the door open? So we need this in order to live and interact with each other in a reasonable and safe way. And as AI becomes more important part of human lives, it's essential for AI to understand the human needs and actions better as well. So here's an example of the atomic knowledge graph. Given the center event, such as X repels Y's attack, human can reason about all these different causes and effects almost on the instantaneously. So, for example, maybe she repelled someone's attack because she wanted to protect other people or wanted to protect themselves. We don't know which is true for sure without additional context, but we can immediately narrow down the possible causes or her intents of repelling someone's attack. Probably it's not because she wanted to learn deep learning out of a sudden. And then before then, she probably needed to train hard and know something about self-defense. And some of these inferences are about effects or post conditions. So for example, she might feel angry, she might want to file police report. Her heart might race. The attacker might fall back, might want to attack back, might feel ashamed. So different types of inferences about emotional reactions and voluntary or involuntary acts that might happen. And then some of these inferences are about dynamic state changes, whereas some of these are about static facts or properties or people's personalities that tend to be more static. So maybe she's skilled and brave and strong in order to fight back. And so this line of research aims to address concerns about deep learning doing only curve fitting. And we somehow need to teach AI causes and effects. And so this graph has today more than actually a million triples of if then rules. And you might wonder how we created that graph. So one possible idea is to mine such knowledge from unlabeled text, but there's a bit of a concern, actually, major concern due to reporting bias that um, AI reading lots of news might conclude that humans murder each other 4 times as often as exhaling because of the reporting bias. So in our work, we crowdsourced all the knowledge using Amazon Mechanical Turk as a platform. And at this point, it's important to note that there are key differences compared to the existing knowledge bases. So a lot of existing resources focused on knowledge of what, especially taxonomic knowledge, such as A is a type of bee, like a penguin is a type of a bird. Um, some of these resources did have other knowledge as well, but still, um, predominantly, when you look at the proportion of knowledge, a lot of them focused more on taxonomic knowledge. And then some of most of such resources, except ConceptNet, aimed to represent knowledge in logical forms. So, for example, here's one example. And the problem with this kind of a logical form, this is an example from Gordon and Hobbes. And it's a thick book with like about 3,000 of handwritten common sense rules that look something like this. The problem with this type of knowledge representation is that it's hard to understand even for humans, and it's difficult to incorporate this to other deep learning models. So, in contrast, we opted for representing everything in natural language. And in fact, this is how humans talk and think as well. We tend to rely on language for thinking and reasoning as well. And we focus on knowledge of why and knowledge of how. In other words, really viewing a bunch of a great deal of inferential, intuitive reasoning as knowledge, almost a pattern matching. And in fact, that was the repeating theme in the part 1 as well, which was that we invoke language a lot for intuitive reasoning. A lot of it is reactive and almost memorized patterns about how the world works. So I told that, and then we have visual common sense graphs that I'm going to talk about uh, after atomic as well. So Comet is the common sense transformers that are built on top of a symbolic knowledge graph such as atomic. And this starts with this philosophical question about whether atomic is large enough. And so when we think about the universe of knowledge that you and I share, it's it's likely, my speculation is that it's likely that atomic is only a small, tiny corner of that universe of knowledge. And then the next question is, do we have to really explicitly enumerate them all and then store them all? My personal speculation is that no, we should not, or we don't need to. For example, if we think about whether elephants are bigger than butterflies, we can answer that question without having to store that explicitly somewhere in our mind. We can just think about it and answer that on the fly. And that's exactly what we need to do, because it may be that the space of common sense knowledge and reasoning is almost infinite. And it's the best if we learn a model that can reason about such knowledge and reasoning in the way that humans do. And because we were using language for knowledge representation, now we can do transfer learning from language to knowledge. So we can use atomic to pretend that we have access to only part of it and then try to regenerate the missing part. And so Comet is going to do transfer learning from language to knowledge by starting from pre-trained language models and then continue training on atomic as if atomic is additional text corpus when such that we convert atomic knowledge graph into lots of text strings like shown here. Given some context event, we encode particular type of common sense knowledge reasoning, and then we generate common sense inferences. So we do that using transformers, and it turns out the resulting model, COMET, common sense transformers, to generalize well on out of a domain examples much better than we realized at the time of our paper. So the demo is available. And if you want to demo or try the Comet model trained on Atomic, this is what you need to click. And then you need to type in some event that you want to reason about, such as Sarah repels Jack's attack in a chess game. But if you want to try Comet trained on ConceptNet instead, there's a button for that as well. So turns out we can give events like John gets into an accident instead of a person X gets into an accident, which is the textual format in Atomic, because Comet was previously pre-trained on natural language text in large amount as well. That's actually based on GPT or GPT-2. We tried both versions. So Comet doesn't mind if we just suddenly say John instead of person X. And the output here is that as a result, person X, which is John, might want to call 911 or get medical attention. And this type of reasoning is great because the word like 911 or medical do not even appear in this input event. So the model is able to learn to reason about what might happen in the future, what people might want to do next, even though such words do not appear in the context event. And it can also generalize to reason about out of a domain examples such as this. Sanya rides into the sunset on a motorcycle after solving AI. And this is an out of domain example in the sense that it's more complex than typical atomic event. It has more complex relative clauses in the sentence, and also there's nothing like a solving AI in atomic. As a result, the prediction focus a little bit more on the motorcycle than AI, solving AI, but nonetheless, the predictions are fairly reasonable. Here's another fun example. Gary breaks the world record for most controversial tweet. So Atomic doesn't include anything about tweet, let alone controversial tweet. And of course, there's no people's name in Atomic, so it doesn't know which Gary we might even be talking about. But so Gary wanted to be famous. Maybe Gary needed to do some research, write a book, write a blog post. He might be seen as someone famous, proud, influential, successful. And then also he might, as a result, feel proud. He might want to celebrate and he might become famous. So as many of you may have heard, Gary Marcus has a lot of concerns about deep learning, especially neural language models, because when he tried talktotransformer.com, which I believe was based on GPT-2, and gave this prompt in boldface, which says, "What happens when you stack kindling and logs in a fireplace and then drop some matches? Is that you typically start a..." And then GPT-2 continued to say some nonsense. But that's really because GPT-2 at the end of the day is not a knowledge model, it's a language model. So if you try the Comet demo by typing Gary stacks kindling and logs and drops some matches, then you get reasonable predictions, such as to start a fire. By the way, these are shown in the order of decreasing probability score of that generation. And again, this is out of a domain example, because if you search atomic, there's nothing quite like this in the database. So Comet really generalized out of atomic. And let me show you some concrete example of the abstraction that Comet seems to be doing on top of atomic. So let me show you how to search atomic. What you do is first you click this part, and then um, in the explore the text box, what you're going to do is type just any one content word, such as Disney in this case. And if you wait for a few seconds, the system will automatically show this Dropbox drop down list that includes all the events, center events, the context events that are in the atomic knowledge graph. So some of these are in the training data. Actually, everything is in the training in this case. So it's also going to show whether the events are in the training or dev or test set. And so you need to click any of this, or you can write down something on your own, but usually you do need to write things that match the text of that event quite precisely. So I recommend that just type one content word and then see what's in there. So you can search atomic whether it knows something about conscious self, and it turns out it doesn't know much about conscious. It knows about self-conscious or unconscious, but it doesn't know about conscious. And then when we do this, when we look at what people annotated, so this is atomic knowledge graph, portion of atomic knowledge graph about this event, self-conscious. People wrote things like, maybe that person ate too much food, might be seen as awkward, things like that. And if you compare that to Comet prediction, it turns out Comet does not just memorize what's in the atomic, but does some sort of generalization. So here we say that instead of eating too much food, Comet generated that maybe the person did something embarrassing, something wrong. And in terms of how the person might be seen, there are additional words that were not in the annotation, such as nervous, shy, and insecure, timid. These are all pretty reasonable predictions that were not even part of the original atomic knowledge graph. So we found that instead of just memorizing the original atomic knowledge graph, Comet does fair amount of generalization and abstraction. So as a summary view, what Comet does is basically this combination between self-supervised learning of observed knowledge in language models together with additional supervision, which follows more of language model training style, the objective function that's in the form of language model training. But nonetheless, it's based on declarative knowledge that humans do have a lot of access to. And in fact, when you think about this atomic knowledge graph, it's almost resembling the kind of descriptive or declarative knowledge that people talk to their child or babies when they're young. We do talk about a lot of the things about why people do what they did. A lot of obvious things are spoken out loud and explicitly for young children. And so perhaps we need to do that for deep learning as well if we want them to have some level of common sense knowledge as well. And in doing so, we view we use language as a symbols instead of a logic, because by doing so, we can do transfer learning from language to knowledge. And we focus more on causal knowledge, causes and effects, because the inferential knowledge, a lot of our basic intuitive inferences are more of a knowledge, memorized pattern matching. And then finally, by using neural representation in the end, we found that it generalized well to compositional and previously unseen events. And if you think about how we might do this for non-neural method, like if you just had access to atomic knowledge graph but no neural uh, models, then it gets much harder, because for previously unseen event, even if we extract some potentially relevant atomic knowledge graph parts, and even if we could somehow parse it correctly, either through syntactic parsing or semantic parsing, none of them will be, uh, I mean, using them, we cannot really figure out computationally how to compose them into new predictions for previously unseen events. So it seems to me that in the end, neural models are, especially based on language models, are the way to go for learning uh, common sense knowledge models. So building on these two, we now have a new version that significantly expands on these original atomic. So not only we have everything that used to be in atomic, which included, for example, X gets X cars repaired because as a result, maybe X wants to call Uber for a ride or pay the bill. So this is atomic knowledge. Now we have additional new knowledge for physical entities as well. So for example, money can be used for paying repairs, but so that's a stereotypical use. We also have a non-stereotypical use cases, such as money can be used to fold into origami. And what's it's made of? It's made of paper. We also have more event-centered knowledge as well. So, for example, um, after you repair a car, maybe you have to drive. Well, actually, I reversed. So you drive an old car, and then maybe you end up having your car repaired. And then this one is about hindered by or counterfactual situation in which this event couldn't happen. So you cannot get your car repaired if your car is totaled completely or it costs too much. Yep. So we have a lot of this, and it amounts to a 1.3 million common sense if then rules described in natural language over 23 different types of inference types. And the paper talks a lot about different ways of evaluating this compared to other existing knowledge, both the symbolic and neural. But let me just highlight one thing to answer this question that you must have about how much does GPT-3 knows already. So to give you um, some like a perspective here, though, the Comet in our new model, we instead of using GPT-2, now we use BART instead. And this is more than 400 times smaller compared to GPT-3. Of course, Comet was trained on this atomic knowledge graph, whereas GPT-3 only read a lot of web text. And so with that in mind, GPT-3 does really well only with a few shot examples, achieving 73 accuracy based on human judgments on the common sense predictions. And that's a major improvement over GPT-2. It's not apple to apple comparison in that GPT-2 is a zero shot, not few shot, but still the jump is real impressive. And still, if you want to do much better, we can use Comet, which is also much smaller. And by the way, the evaluation here is set up such that it's somewhat adversarial for Comet in the sense that the test examples are as different from training examples as possible. So if you actually gave more familiar examples similar to training examples, then the performance would be higher than this. But here we are showing the sort of like what happens when you really try to evaluate ConceptNet using test set that differs as much as possible from training set. Okay, so let me next talk about the visual ConceptNet, which aims to address declarative common sense knowledge in the visual space as well. In order to motivate what we do, let me first to show you this example. And let's think about what state-of-the-art object detection might do for this image. And so it's going to detect a lot of objects correctly, but this set of objects says nothing about the original image. And so people started adding more annotations to that more complex annotations by adding additional nodes and edges, making it more like a graph. Probably we're moving into the right direction. However, again, if you look at this set of words connected in a graph structure, we still don't really see the story of the original image. And so the next step is using the full sentence for image captioning, but the previous image captioning focused more on what people are doing a little bit more literally. But still, it doesn't really explain why they are doing what they're doing, because that's really, and what happens before and after, because that's really how we understand visual scenes. We see a story, not just the literal content of that still image, but really what is happening in that particular moment in time. So, as highlighted in the part 1 of this class, um, the temporal reasoning about past to future, is really a critical aspect of system one reasoning, and that's what we subconsciously does all the time. And so, in order to capture that in this work, grounded on any particular person in an image, the goal is to predict all of these octopus tentacle like predictions, mimicking what humans do instantaneously. So, given an image, what we want to do is to reason about the dynamic context of a still image. And in order to enable this, we annotated not only one image, but many more, so that what it culminates to is this connected graph where when you see a scream for help, for example, you can trace back in what sort of images you might think about or predict screaming for help. Now, this is quite interesting case of human intelligence because it's a visual. Images are images without audio, so we are not actually hearing screaming for help. But nonetheless, crowd workers do imagine hearing this auditorial event that they cannot hear. And similarly, crashing the car can be linked to images when uh, images that were taken after crashing the car. So we actually don't see the moment of crashing the car or before crashing the car, what appears to be before crashing the car, without actually seeing the moment of crashing the car. So as a human, we can sort of anticipate what may have happened before and after. And that's what this new knowledge graph, multimodal knowledge graph, is uh, annotated with. So quickly, the data set statistics is that it's based on 60,000 complex images, and they're all from movie scenes, and a bunch of different kinds of common sense inferences are annotated. And because the annotation is rich, it supports different definitions of a task. Now, in this talk, I'm going to just work on this particular definition, but in the paper, we explore additional ways of defining input and output. But for now, let's just say input is an image, and then person grounding, and then the event describing that person at the moment. Given that as an input, can we predict everything on this side, which corresponds to the output, about people's actions or motivations before and after. So not surprisingly, our model builds on pre-trained language models, because transformers basically are the winning architecture currently for any language and vision leaderboards as well. And our approach is that we encode both the visual context as well as textual context, serialized, because transformers always take the serialized input. And then we try to generate common sense predictions in language as an output. And so we do want to do sanity checks against the spurious biases, though, because what we learned from other language and vision data sets from the past is that you don't want the data set to be solved too easily by either nearest neighbor baseline, which sort of implies that your data set might be overpopulated with the similar instances. And then we also don't want the QA problems solved only by looking at language instead of looking at images, because what's the color of the banana? It's almost always yellow even without looking at the image. So with that, so in this uh, uh, task definition as a sanity check, what we can do is remove image, just to look, give this text information, and then see whether the transformers can do too well in this setup. And it turns out either nearest neighbors or language only baselines do not do as well as the multimodal representations. So that's a good thing, that data set provides enough of a diverse challenges that language only models cannot do overly well. But based on human evaluation, the common sense predictions could be really better in terms of accuracy. So a lot more work to be done. And here are still some better examples that the model can generate. So for example, um, in this case, so person one is the server putting a platter on the table at an outdoor restaurant, and because before person one needed to perhaps buy groceries, get up from the table. And this is the prediction from language only baseline. So the language only baseline doesn't know that this person is server only based on this text. So, but usually the server doesn't do this kind of actions compared to, I mean, server didn't even sit on the table usually. So the serving person probably do not get up from the table. And the vision and language model does recognize that, oh, perhaps this person is the serving person. So now it talks more about properly that he may be hired as a waiter and wait for everyone to sit down and then receive an order. So there are more similar examples. I think I'm going to skip over this part and then briefly conclude with the summary that it's a new resource that supports research that aims to close the gap between perceptual level and cognition level, or intuitive common sense reasoning level understanding of visual scenes, complex visual scenes. And the dataset supports new tasks and models beyond what are briefly presented here. Finally, let me give you yet entirely different kind of a resource that is called the Social Chemistry 101 for social norms and moral norms. And so let's just start by what GPT-3 knows or does not know. So if I prompt GPT-3 by running a blender at 5 a.m. is rude because ... it says you can wake up the entire neighborhood. I don't think a blender can do that, but anyhow, you can only do it if you are making a thick smoothie and need to incorporate some ice. So it's kind of funny, cute, but no major harm made. But if you challenge or trick GPT-3 with prompts like this, it's okay to post a fake news if it's going to say things that it might have learned from the web data, but it's not quite ideal. So this raises these concerns about how neural language models are a little bit tricky to be used in actual applications because of this kind of morally questionable generation. Sometimes it also generates toxic language that can be harmful against, especially people in the underrepresented groups. So we somehow need to teach AI, find a way to teach AI with people's values and ethical norms. And I do not think increasing GPT-3 with more data and more parameters will cut it. It's unlikely that that's how we achieve that. And so that's where this social chemistry come along. And importantly, as we will see, we need the full scope of language. This is a repeating theme in this part two, which is that for visual comment as well, we needed the full scope of language because simple words or graphs of words were not sufficient for really describing what's going on in an image. And similarly, for social norms as well, we need full scope of language. Let me give you some example about how complex humans' social norms are. So asking my boyfriend to stop being friends with his ex, given that situation, different people come up with different rules of thumb about what they should do, what someone else should do. Some people may think it's okay to ask your significant other to stop doing something you're not comfortable with, but others might highlight other aspects of the situation, saying it's not okay to tell someone else what to do or whom to spend time with. Some other aspects might be that you should make sure that your significant other doesn't feel like a lower priority. So really totally complicated, and different people have different priorities. So some people prioritize more on authority. Some people prioritize more care and harm, loyalty. And so and depending on whom you ask, do you ask your boyfriend their opinion or his ex's opinion or the narrator's opinion? So really, depending on which person in an event we ask this question, we get entirely different um, preferences about what kind of social norms described in rules of thumb they might prefer. So for any given concrete situation and one rule of thumb, in this work, we provide a bunch of semi-structured annotations about different stuff. I'm not going to go into the details of the annotation other than highlighting that in total, there are 300,000 of rules of thumb in our data set grounded on hundreds of thousands of real-life situations. And each of these situation ROT pair is annotated with 12 structured attributes. That includes the social judgments, cultural pressure, anticipated agreement, legality, and moral foundation theory-based dimensions, which, by the way, has to do with this book by Jonathan Haidt about why people are divided by politics and religion, because they emphasize on different moral values. Okay, so because the data set is large, of course, you can download the pre-trained language models and train these to do lots of different things. So we computed many tables of rows and columns, but let me just skip over this part and let me just highlight the important high-level perspective that's behind this work. So first of all, safe communication requires understanding people's norms. And there may be different types of norms, like social norms, moral norms, ethical norms. They're a little bit different. They do overlap, but they don't separate out in a clean-cut way. So in our work, we just broadly encompass all of them through concrete, grounded examples. And there's this question of what are the fundamental values and who do we decide which are these ethical values that people should care about? What we decided to do after studying different types of ethical research outside the computer science, we decided to take the branch of research called descriptive ethics. What that line of research does is to ask people what they do, what they would do in some concrete situations. And this contrasts with the prescriptive ethics, which is more like top down as opposed to bottom up. So, top down, thinking about what are 5 or 7 fundamental dimensions of or values that we have to um, respect. And the problem with the prescriptive direction is that who's going to decide? Do humans ever agree on magic 5 or 7? Depending on their religion or cultural backgrounds, people do emphasize on different types of different dimensions of moral values, ethical values. So we decided that we're going to take the bottom up approach, asking people what they think. And there's also this question of the problem with this prescriptive approach is that even if we somehow magically find agreement among everyone that there are 7 magic dimensions that we should care about, it's almost useless for AI because AI may not know what to do with the 7 dimensions when confronted with a particular situation, which oftentimes also present moral dilemma. So, in order to teach AI with broad scope of complex situations that people encounter, we decided to um, make this resource that are grounded in particular situations. Okay, so that's the second part of the talk in which I presented 3 different flavors of research that can be by and large summarized as the direction of research that aims to have declarative knowledge for the purpose of knowledge modeling. And then finally, let me mention briefly benchmarks and the need for algorithmic bias reduction. So 2 years ago, well, that's already 2 years ago now because now it's year 2021. DARPA was planning to create new program on machine common sense and asked my group whether we might be able to make a challenge data set. And we were excited to do so and got a little bit carried away to create not only one, but more than 7, actually. So we wanted to have more than 7 because we wanted to cover a broad spectrum of common sense challenges. And some of these we've seen already, like objective common sense reasoning. But let me just highlight other stuff a little bit. Physical IQA is about testing knowledge of affordances and physical attributes. So, for example, which household item can I use to roll out bread dough? Wine bottle or bread mixer? Maybe language model will find the bread mixer appealing because it doesn't know that wine bottle has that particular shape, which makes it so it makes only sense to use wine bottle, not bread mixer, for rolling out your bread dough. So another data set we made is called the Wino Grande. This is basically a larger version of a Winograd schema challenge, which is about pronoun resolution. The large ball crashed right through the table because it was made of steel. If you say steel, then it refers to the ball. Whereas if you say styrofoam, now it should be resolved to table. And so it's a grande because it's grande sized with this many instances. And then Cosmos QA is another data set where it's a reading comprehension data set that requires common sense reasoning in order to answer the question. So here the context says it's a very humbling experience when you need someone to dress you every morning, tie your shoes, and put your hair up. Every menial task takes an unprecedented amount of effort. So, what's going on with the writer? And the context doesn't say what's going on, but we can infer that the writer may have a physical disability. I mean, it sounds like it's a new situation the writer is dealing with. And so we do this kind of reasoning due to the fact that we have this model about how the world works, how people work, the common sense knowledge about the physical and social rules of thumb. So, but we learned a lesson by creating all these data sets, which I want to now share, especially starting with this HeLa swag, which is a follow-up paper from swag. And when we initially made this swag data set, we thought it may be too hard, but soon after BERT came out and just solved it. And then New York Times article basically said, finally, a machine that can finish your sentence. If that's true, I would be delighted, but it's actually not true that neural language models can reliably finish your sentence. But it pretends to do it really well on the leaderboard. So what's going on? Well, what's going on is that it's like clever Hans horse situation where neural models are doing really well on exam problems, but for questionable reasons, almost solving exams right for the wrong reasons. And so the takeaway message is that, first of all, data set, if in the multiple choice questions, then it must be debiased by algorithm because humans are not capable of seeing all these biases anymore. And then the data set must evolve to get with to uh, in order to match the evolving state of the art models. Let me give you a little bit of quick algorithm intuition about what we can do with bias reduction. So in our earlier version, what we were doing is that if we design multiple choice questions, so each column corresponds to different problems and each rows correspond to different answers. And blue, the first one is correct answer. The rest are the incorrect answers. So we can split the data randomly into training and test, and then train a model that we're going to use as a filter, adversarial filter, because we're going to use this model in order to see how hard this test set, temporary test set is. And whenever we see that the model is doing too well, we are going to replace that question, the answer, with a new one so that it becomes harder. And so we can keep doing this iteratively in order to make the data set harder and harder iteratively. So we do this until convergence, and the resulting data, which we call as AF the data, uh, importantly holds identical distribution across the training and test. So oftentimes when people talk about adversarial algorithms, they might be talking about the test set being very different from training data. But in this work, the resulting data will maintain the identical distribution across the training and test. And also importantly, we found that human performance remains high even after we AF the data, while AI performance drops down significantly. Now, when that happens, when human performance remains high, but AI performs much worse, is when we should worry that perhaps the leaderboard performance matching human parity was all inflated because of the spurious biases that the neural models were able to latch on. So perhaps going forward, one uh, possible adversarial evaluation framework that we might need to incorporate is that it should be sort of a collaboration between humans and machines, or composers and critics, where composers generate questions, but critics might need to validate whether the exam questions are too repetitive or subject to spurious biases. And in fact, these critics might need to be a combination of a human and machine, and these composers might also need to be a combination of a human and machines, though, of course, the different data set has a different uh, exam problem generation strategies. In the case of a SWAG, we were using LSTMs as a composers and LSTMs as a critics. And we quickly realized that we do need to replace these models to match the evolving state of the art, or else we end up creating data set that's filled with spurious patterns that these strong pre-trained models can latch on. So benchmark must evolve with um, together with the evolving state of the art. And this is quite new situation that we're dealing with, because in the past, even a few years ago, a data set once created was remaining unsolved almost for a decade or 2 decades. And it's only in recent few years when we realized that the shelf lives of leaderboards are becoming shorter and shorter without necessarily solving that particular task at hand. So in our work, Wino Grande, not only we made this new data set, we also actually introduced this new adversarial filtering algorithm called AF Lite. And this AF Lite has been further investigated in our follow-up work presented at ICML. So let me give you very, very brief, intuitive description of what these are all about. So the original flavor of AF algorithm is what I described a few minutes ago, which were used in these papers. And then in our new papers, we discuss how you can actually do it with much less computation. So in the original version, we had to retrain the filter many times over. And if we use BERT as a filter, we have to retrain BERT many times over. Whereas in this new version, we don't need to train BERT more than once. In fact, BERT is trained on a very small fraction of data, like maybe 7%, some small fraction of the data, and then it's going to be fixed. And it's used only to compute um, some like rough word embedding, contextual word embedding of the exam problems. And once we have that, we train linear classifier. This trains really fast because it's linear classifier, computationally very light. And we found that this version, iterative version of linear classifier, works just as well as the original flavor. And it turns out the models trained on AFD data are also more robust when tested on out-of-domain distribution. So when tested on Hans or NLI diagnostics or adversarial NLI, these are all NLI data sets that are different from SNLI and created by other researchers. And we found that the models trained on Roberta, trained on SNLI is blue, and Roberta trained on AFT data, that's a smaller data, in fact, does perform better on these more adversarial out-of-domain distribution. And we found the same pattern for ImageNet as well. So ImageNet A is a data set that's adversarial. And again, we see that models trained on AFT data show more robust out-of-domain distribution performance. So to summarize, we've, as a field, we've really relied on multiple choice QA data sets as leaderboards a lot because it's easy to evaluate. But whenever we do that, it seems that neural networks can immediately latch on spurious patterns in that data set. And such models don't do very well anyway on out of domain or when they are evaluated generatively. So going forward, if we are doing multiple choice questions, then we might need to research more actively on adversarial bias reduction. And then in addition to that, there may not be enough because the complete bias reduction seems nearly impossible. And so we need to think more about generative evaluation. And in fact, even for measuring human intelligence, usually we don't really believe multiple choice questions as the reliable measure of human intelligence either. And we really want to see like how we are able to generate questions, answers as needed. And even when we think about these earlier examples with monsters in a tunnel, it's really unreasonable to assume that some oracle will always provide us with four magical choices to choose from. In real life scenario, the AI really needs to be able to just come up with its own hypothesis without relying on some oracle presenting four choices to choose from, where one of which is guaranteed to be correct. So to summarize, a few closing remarks. Common sense is certainly a new direction of research that became popular only very recently, because if you search the word common sense from ACL anthology, most papers are either from 80s or from the past few years. And in fact, when I was thinking to do research on common sense several years ago, I was told not to speak even the word because nobody will take me seriously. But then I realized that past failures are completely inconclusive when they were based only on weak computing power, not much data, no crowdsourcing, not as strong computational models, and they were based on logical forms instead of language as the representation medium. So I think a lot of the research done by smart people are still inconclusive if they're from 70s and 80s, because we simply didn't really explore the research well enough. Still, it's a moonshot research, so we don't know the full path forward quite yet, though we have a lot of interesting and exciting results that encourage us to move forward. But one thing for sure, it's unlikely that just making GPT 4, 5, 6, adding more data with more parameters will cut it, in the sense that we cannot reach to the moon by making the tallest building in the world 1 inch taller at a time. And then commonly asked questions about common sense is that, well, do we really need language? Because my dog clearly has common sense. My baby has common sense without language. Therefore, maybe language is not that important for common sense. I think the answer is it really depends on what kind of common sense you are trying to replicate with AI. If it's only dog level or baby level, that's one thing. But if it's for more broadly humans, which by and large include adults, then we do need to incorporate language as well. Another commonly asked questions or concerns is that some concepts really require embodiment. For example, that juicy, crunchy feel you get when biting into an apple cannot be learned without embodiment. True. But some people seem to assume that therefore we should just forget about language based common sense models altogether. Let me give a counterexample to that line of argument by pointing out that as a human, we learned that a tiger can eat a human being without actually experiencing it in real life. We didn't have embodied experience of being eaten by a tiger, nor did we even watch YouTube videos of that event happening. Probably it's unethical to have such a video available online. So, drowning in the ocean, we probably, many of us probably didn't experience it, hopefully, but we do learn that kind of a concept through language. And in fact, even if we were to build a robot that can bite into an apple, it's unlikely that they will ever have the same exact kind of experience that humans do. Even if we were to build a simulation environment in which AI can experience it, it's likely to be some reward function that some engineers wrote in some numbers, which is not any more real compared to the language description of juicy, crunchy feel. So I really don't see how that line of reasoning can actually work against the language only models. Having said all of this, I'm not against multimodal representation learning at all, because I mean, I also worked on Visual Comet and many other um, multimodal representation learning as well. But what I believe in is that we do need to think about the trade-offs between the coverage of a concept and the richness of a multimodal and embodied experiences. And the more of the embodiment or multimodal experiences we can include into the representation, it seems that the coverage of a concept shrink drastically, because we currently do not have a 3D environment where people drown in the ocean, for example. And so it's likely that we do need to pursue all three different types of or many different types of research that combine different modalities at different level of conceptual coverage. And in doing so, we also need to think about how we are going to really connect these different types of learning mode. And in doing so, my speculation is that language might provide a powerful representation medium in order to learn humans' embodied experiences as declarative knowledge. So it might be some gluing conceptual pointer. So uh, we are reaching to the end of this part 2 of the class. And let me make final remarks on language, the connection between language and reason. So I really enjoyed reading this book, The Enigma of Reason by Hugo Mercier and Dan Sperber, which also talks about system one and system two reasoning. And the book highlights how intuitive inferences is a great deal about extraction of new information from the information of already available. And this is very similar to abductive reasoning, abduction, which is about generating new information that's not necessarily um, true based on premise, but likely to be true based on the premise or partial observation. And what was really fascinating to me about what this book said is that we invoke system two reasoning not to guide ourselves to make an important decision, but to justify ourselves in the eyes of others or to convince others. And so reasoning two system two reasoning solves the purpose of communication. And if this is all true, it really implies that language is such an important part of system two reasoning as well, which was alluded already earlier when I highlighted how crafting um, rebuttal for ACL or iClear papers require very difficult, hard thinking, which is unlikely to be intuitive reasoning. And in fact, it's really fascinating how our reasoning is system two reasoning is built on top of intuitive inferences. They're not really clean cut separable. They are intermingled in a complicated way, but the conventional meaning of logic plays at best a marginal role. And this is a point also repeated by this other book, How We Reason by Philip Johnson Lard, who's probably better known for this other earlier book he wrote about mental models. But this is the recent version that I found really insightful about how people reason and how it's not quite the same as the conventional logic that we are more familiar with. Um, anyhow, last but not but the least, this class, although ran over 2 hours, we're not able to cover a lot of work in the field in recent years on common sense. And that's better covered by this ACL tutorial given by Vera Schwartz, Martin Sapp, Antoine Boslet, and Dan Roth together. And so, by the way, Dan Roth is a professor at UPenn, of course, and Antoine is studying his faculty position at EPFL soon. And Martin has been at UW, but and Vered at AI too, but they're on the market this year, so they might be moving elsewhere next year. Fingers crossed. So that's all for now, and I hope to see you at the QA sessions. Thank you. Bye.